So everyone is back. So it's my pleasure to introduce the second talk of our morning. It's Katrin Gelfert from the Federal University of Rio de Janeiro, and she's going to speak about heterodimensional cycles between measures.
Okay, thank you. Thanks to the DinAmicIs and the organizers for the invitation for this nice meeting this week. I am talking about my current playground to the study, trying to understand the space of invariant measures. So, in my talk, well, there do appear invariant, but most of the time there will be ergodic measures only. And the reason is precisely to understand the interplay, how ergodic measures spread in the space of the convex closure of the invariant measures. And in particular, we would like to understand the space of invariant measures beyond the hyperbolic setting. So in my talk today, I will mainly talk about diffeomorphism. So I forgot to, this is a current project with Lorenzo Diaz from Buki and Christian Bonatti from Dijon. So we were inspired by, everybody, well, many people are inspired by the work of Sigmund, which in the 70s, and there are several other papers related to, not just by Sigmund, many people around that time try to understand the measure. So the main result, one of the main results of Sigmund is that if you have a system with specification, I'm not going to define a specification property, which is an abstract property for a continuous map on the metric space, but in a set of diffeomorphisms, it essentially means that you have the dynamics of a basic set. So if you have a basic set, then it's conjugate to a nice shift of finite type, and you essentially can describe all the dynamics by your your dynamics of the diffeomorphism on the basic set by the dynamics on the shift space. And Sigmund showed that, for example, so he had several results, but for example, if you take two measures, ergodic measures mu and nu, and you take the convex combination, this gives you a segment of invariant measures, not ergodic, but then he showed that any of those measures in this segment, and I will denote in my talk this segment just by this, so this would be the convex combination of these two ergodic measures, then he shows that any of those measures can be approximated in the weak star topology by other ergodic measures. He proved that by periodic measures. And the proof was so it's kind of intuitive. You take think of, instead of specification, think of your shift space, complete shift for simplicity, and then an invariant measure okay, he also proves generic points. So take any orbit, any collection of orbit pieces that make up your measure, and then in your shift space you construct by hand your ergodic measures by concatenating these orbit pieces, and then you close up to get your periodic measure. So this is, in very rough terms, the proof which he does. So whenever you have symbolic dynamics which describes your dynamical system, then you're fine and you have these kind of properties. So in my talk, so we would like to, in the long run, to understand what happens in a non-hyperbolic setting, so beyond hyperbolicity, beyond simple basic sets. And we are also interested I hope that I can explain some of the ideas and results we are interested in robust settings where results can be obtained. So we would like to understand when, in general, a simple convex combination of two ergodic measures can be approached by ergodic measures. Okay? So in my talk today, I will focus on a particular case. I will assume that consider C1 diffeomorphisms and also assume that they are partially hyperbolic and that they have a splitting into 3 subbundles. So a strong stable bundle, a strong unstable bundle, and at some point it will be important that they have, you have existing strong foliations associated. And I will assume that the center bundle is one-dimensional. And at some point, my examples will live in a 3-dimensional manifold. So this setting has some reasons that we choose this particular setting, because it's already beyond hyperbolicity, but it's also kind of still simple enough to prove things. So in particular, if you look at the one-dimensional center bundle, so if you go beyond hyperbolicity, you study Lyapunov exponents, and in this case, the center bundle is one of the oscillated directions. So if you want to check for hyperbolicity, you just need to know if your Lyapunov exponent of a measure in the center direction, which is just the restriction to this bundle, is negative, then your measure would be hyperbolic of a contracting type. So there are one more dimension which is contracting, or if it's positive, then your measure is hyperbolic of expanding type, or maybe non-hyperbolic, so if this integral would be 0. And the advantage of the bundle being one-dimensional, while you're just dealing with the continuous function, dealing with Birkhoff averages makes some things easier. Okay, so you have your general space of ergodic measures. And the convex closure of this would give you the space of all the invariant measures. And now, because of this, in this hypothesis, your space of ergodic measures splits into those which have contracting. So this is the set of measures where the set of measures such that the central exponent is negative. Then you have those where this average is 0. So this would be the subset of non-hyperbolic measures, and the corresponding ones where your exponent is positive. Okay? So, well, there are some precursors. As always, there are people study things in the past, and we are learning by the experiences of the others. So let me just give you a few remarks on the literature, what people have done. For example, in the case of these partially hyperbolic diffeomorphisms, usually there are some other assumptions put. For example, in this context, one assumes that the strong foliations are minimal. Every leaf is dense. This is a quite common assumption. And then for some constructions, there is also the existence of so-called blenders. Blender horseshoe is important. But let me not give all the details on the results, but just some references. For example, to study the ergodic measures with 0 exponent, non-hyperbolic measures, and the approximation by hyperbolic ones. So there are, well, myself with Lorenzo Diaz and Michael Rams. Then with Bruno Santiago from UFI. And there was also Yiwei Yang and Xinhua Sheng. And Sheng was a student of Christian Bonatti. So they also have some work on this. where they proved that there are measures, any measure here can be approximated weak star in entropy by hyperbolic ergodic measures from either side. So there are some assumptions, as I said already. Let me not give all the details because this will not be my focus. My focus will be looking at the hyperbolic sets. So I would like to take one ergodic measure here and one ergodic measure there, take this segment and see if and when and why this segment of invariant measures is approximated. So maybe the talk today is not about a fancy proof, because the proof is comparably simple. I think I see it more as getting the right concept to describe such a phenomenon. So the reason why this happens, and maybe to understand better the nature of some measures, and the measure space in total. Okay, so a key concept is, maybe I have some space here. So this is which chalk I can use? Yeah, okay. Okay. So a key concept is a cycle. So two measures are related by a cycle. So two measures, mu, and I will write this tilde. Okay. Related by a cycle if the following happens. So I have the stable set of mu relative to f intersects the unstable set of nu relative to f, and likewise the unstable set of mu intersects the stable set of nu relative to f. And here, let me just define the stable. The unstable is defined accordingly, taking the inverse. So these are all the sets X, such that the Dirac masses on those points converge weak star to the measure. Okay? So this is I would see as a stable set of a measure. And if there is this pairwise intersection of the stable and unstable sets, and I will talk about a cycle between these two measures. So you can you can use this concept for any type of measures, assuming that they have generic points. Sigmund, for example, showed that this approximation not only holds, but there's a rich structure of generic points, for example, which is not trivial in other contexts, that any of those invariant measures have generic points. Okay? So, okay, so maybe one more word about these cycles. One says that the cycle is equidimensional. Oh my God. Oh. If mu and nu are of the same type, so I didn't define type, I have, as I said already in this partially hyperbolic setting, the center direction determines if a measure is hyperbolic of contracting type, non-hyperbolic, or of expanding type. So if they have the same nature relative to C, being hyperbolic and of the same nature, then I would say that they are of the same type. Okay, and then I say that this cycle is equidimensional, otherwise is heterodimensional. That means if they are of different type, hyperbolic and of different type, then I will say that they are heterodimensional. Okay, and to continue one more moment with the historic comments. So if you have if you ignore this rich splitting and look at only a pair of ergodic measures of the same type, so with Jairo Bocchi, Christian Bonacci, we got, there are some mild hypotheses, which I'm not going to give all the details, that say that the following is equivalent. For measures, let's say, of expanding type, so of the same type of hyperbolicity, the first property that there exists a T such that this sum is approximated by ergodic measures, which then necessarily have to be in this set. Second, the whole segment between the two is contained in the set of ergodic measures, taken the closure. And three, mu and nu are homoclinically related. So the concept of being homoclinically related is a bit different from having a cycle. Here you assume that there exist generic points relative to mu and generic points, relative to mu and nu, such that their Pacean invariant manifolds intersect cyclically and transversally. So it's almost the same, only looking specifically onto the Pacean manifolds. So in fact, the concept of, you can also define now an equivalence relation of measures, ergodic measures, looking at this relation of being homoclinically related. And in fact, this was already coined in the paper by Rodriguez-Hertz. Ures, and Tassibi. So they coined the concept of homoclinic classes of measures using the same definition as I just said. And okay, one more result, talking about measures of the same type of hyperbolicity. There is a paper already in 2011 by Abdenour. So all the other papers are more recent. I didn't give the years. So Abdenour, Bonatti, and Crovese, they showed that for C1 generic diffeomorphisms, and looking at two periodic points and their Dirac masses, taking two periodic points of the same type of hyperbolicity, then, and assuming that these are, the points are related, then the segment of these two measures is approximated by periodic orbits in the same class in the same homoclinic class. So this is one result which they prove in the C1 generic settings. So you have this second condition satisfied relative to measures which are in the same homoclinic class. Okay, so as I said in my talk today, I would like to take the mixed point of view. So I would like to take a measure of contracting type and a measure of expanding type and see if this segment is approximated by others. Okay. I have one more one more historic comment. In this setting, there is Bonatti and Chinois Shang. They showed that this can be realized, only that they didn't have a general result. They found, so that they proved that for partially hyperbolic, some assumption on minimality and existence of a blender, that there is an invariant measure sitting on a blender and a measure sitting on some fixed point such that this segment is approximated. So here they only find some invariant measure. Okay, so this is more or less some historic summary of some of the recent results. And I would like to present today, well, I'm not, the following result, which is with Lorenzo, myself, and Christian, is the following. So assume that F is a C1 diffeo, partially hyperbolic, as I said already. Well, okay, the theorem is stated slightly different. C1 diffeo, assume that I have two measures, hyperbolic and of expanding and contracting type respectively, which are related by a Rich cycle, which I did not yet define. I will do this in a minute. Related by a Rich heterodimensional cycle. Okay, then any measure in the segment is approximated weak star by ergodic ones. Periodic ones, indeed. Okay, ergodic. If you have ergodic, then you have periodic in this context. So a periodic measure is one supported on a point of a periodic orbit. Okay. Okay, so this is the main result. We proved this, well, I will give the definition of a cycle in a bit. I won't talk about the proof, which is using Liao's Ganz shadowing lemma. Okay. And my focus is on introducing the concept of a rich cycle, discuss a bit, and present examples. So here there is in the title and also in the names appear already heterodimensional cycle. And of course, this concepts and the ideas and the questions came from the study of heterodimensional cycles. So Christian Bonatti and Lorenzo Diaz are my co-authors, so that's a natural playground, has been for quite some time. So I'm not able to talk about heterodimensional cycles as well as they would, but I learned so far that robust heterodimensional cycles between saddles, between periodic points, they provide a kind of one explanation of how non-hyperbolicity occurs, searches. Provides one semi-local mechanism to explain the occurrence of non-hyperbolicity, and the concept of blenders, which will appear also at the end of my talk, they played a very important role. Okay, so and here we would like to study the measure theoretic counterpart, the heterodimensional cycles between measures, and of course, if your measure is supported on a fixed point, for example, then these two concepts coincide. But one in these studies of non-hyperbolicity, one important fact is the robust property. If you have a periodic orbit which is hyperbolic and you perturb your diffeomorphism, then the periodic orbit will also change continuously. And if you look at the ergodic measure on this orbit, it also will change continuously. And if you have a robust heterodimensional cycle of periodic orbits, then this configuration is, well, it's what in the case they studied is robust, so it changes continuously. If you talk about a cycle of measures, well, first of all, there is no, in general, no think of a natural continuation of a measure, of an ergodic measure. If your measure was periodic, hyperbolic, then of course. If your measure was an SRB measure in, let's say, C2, well, the SRB measure has many other properties which are robust, and hence your measure changes continuously. If your measure is a measure of maximal entropy and you perturb slightly and the symbolic dynamics stays the same, then the same thing holds. But for general ergodic measure, there's no way to define the continuation of a measure. It doesn't make, well, there is no such concept. So what we would like to explore is maybe there are some measures which are different, which survive perturbations. And maybe there are some measures which form a cycle in this way, which also survives perturbations. So our focus was on robust examples. Okay, so let me start with things easy. So I would like to now define the cycle. Okay, the rich cycle. So let's start simple. Let's take two measures which are supported on a fixed point. Let's say mu minus the Dirac mass on some point P, and mu plus the Dirac mass on some Q of contracting and expanding type. So here I have a two-dimensional stable with one strong stable and one stable direction, and the one-dimensional unstable. So as I said, I will switch to three-dimensional manifolds, and that's going to happen now. And here I have a two-dimensional unstable and a one-dimensional strong stable direction. So okay, so if I take this stable, the definition of a cycle, the first one. So let me just write this down here. Then I would need to intersect the two-dimensional subspace with the two-dimensional subspace, and there's plenty of options to intersect the two-dimensional with the two-dimensional space. It's a bit more difficult if you have the unstable with the stable. So the unstable is just one-dimensional, and the stable is also just one-dimensional. Okay, and then you must be very lucky to get an intersection. And an example is, for example, the following case of, let me copy because otherwise it will be a mess. It's the following cycle configuration. That you have your strong stable, strong unstable, and one of these weak unstable coincide with the stable of P, and moreover, this manifold makes a cycle and intersects this table in one point. So this would be a configuration where you do have these intersections. Okay, so this is just a situation of a cycle, heterodimensional, of these two measures. Okay, so here P is negative, Q is positive. So Ridge cycle is also a cycle, but it needs some further properties where the strong foliations come into play. So the strong foliations are the foliations tangent to the strong stable and strong unstable directions from the partially hyperbolic splitting, which I just erased. Okay. So let me give the definition of a ridge heterodimensional cycle between a measure mu and the measure mu minus and mu plus, which already suggests that they are of different hyperbolic and of different type of hyperbolicity, but I will write this down in the definition. So first, I assume that both are uniformly hyperbolic. In the sense that the support of either of them is a hyperbolic set. Relative to F. Okay, which is well, we are not completely happy about our hypothesis we put, but that's the things we could deal with. So one is of contracting type, so meaning the central Lyapunov of exponents negative, and the other one is of expanding type. This is condition 1. Second condition assumes that there is lambda, some compact invariant set, such that its tangent space is has a partially hyperbolic splitting relative to F. So we do not assume that writing down the setting which fits to the theorem. So a priori, you do not need a globally partially hyperbolic diffeomorphism, but you just need some set where your dynamics is partially hyperbolic. Okay. And such that lambda contains the support of mu and of nu simultaneously. 3, for any point in the support of mu minus, and for any point in the support of mu plus, the stable manifold of x minus intersects transversally the unstable manifold of x plus in lambda transversally, and the unstable manifold of, so this is the strong unstable manifold, and the strong stable manifold of x minus intersects transversally the unstable manifold of x plus in lambda. Okay, so this is a refined property of this one. So I have also made some figures relative to this picture. So I would assume that here you have this stable manifold of x minus. So this is x minus, and intersects transversally the strong unstable. So here you had before the stable set, but you wanted the strong unstable of x plus intersects. And in the other case, you had the stable set of x plus and the okay. Strong stable manifold of x minus intersects the other one. So this is what I said, you need some further properties that the strong foliations come into play. Okay, so, and the fourth property was already in the case of the cycle, so this was this non-trivial intersection, which is just that there is some mu minus generic point x and some mu plus generic point such that the unstable of x minus intersects the stable of x plus. And here, these are simultaneously the strong manifolds, strong unstable and strong stable manifolds respectively. Okay, so this is the definition of the rich cycle. I have 20 minutes, no? Yeah. Okay, any questions? Okay, so I would like now to present two classes of examples, which we like personally. There's always some personal preferences, but we like these as a playground, some nice things to start to understand. The first is a class of saddle SRB measures. We are not quite sure that this is you have many, well, my origin is German, so I like to combine names. So it's saddle SRB measures in a C2 robust setting. This is the robust example, which is really robust with the cycles. And the second is a class of skew products. As usual, skew products are easier to understand. They are not diffeomorphisms, but they have, well, they can be seen as a diffeomorphism, but they are not yet as nice as they could be. And there are many things to do, many things still to be done. And they maybe give rise to the concept of an ergodic blender. A blender which has the property of a blender, and a blender is a topological, it's just a horseshoe with very specific topological property, and this would give rise to a concept of an ergodic blender which mimics this on an ergodic level. Okay, so let me give the first class of robust heterodimensional cycles coming from Plugin attractor. So you take your favorite hyperbolic attractor, for example, the Plugin attractor. And from the Plugin attractor, which lives on a surface, so we take a Plugin attractor on a surface and extend this to a diffeomorphism in a three-dimensional manifold. So we get the following theorem. There exists on any three-dimensional manifold supports diffeomorphism, C2 diffeomorphism with some saddle attractor and the saddle repeller, basic sets, such that with saddle SRB measures, the attractor has an SRB measure and the repeller has an SRB measure for the inverses. Well, I will still define what is a saddle SRB measure. And these have the property that first the two measures have a rich heterodimensional cycle, and any G close to C2 close to F also has this property. So in this case, the measures, the SRB measures that saddle SRB measures we consider, they have the property that they do have a natural continuation. So you can talk about these objects for perturbations and the any C2. I will define this in now. Okay. So, okay. So when you have your plug-in attractor, which is on a surface, your hyperbolic attractor, and has the property that, well, it has a kind of linear structure, which is in fact tangent to the unstable manifold. And so you have your points of your attractor, the unstable direction, and transversally the strong stable direction in any generic point of your SRB measure. And the strong unstable manifolds, they fill densely your entire manifold. So they foliate your entire manifold, your entire space. And so you look at this attractor, lambda, of some, let's say, map F tilde on M2. And you know that this has an SRB measure. Let's call this plus, yes, tilde, which is just the equilibrium state of your geometric potential, which is the restriction to the unstable manifold. Okay, so you take your attractor and then you multiply your space with one extra dimension, and you take an expansion which fixes you choose an extension such that it fixes the manifold and is uniformly expanded in this extra coordinate. And then you extend this to a map F on M3. And if you put some assumption, some extra assumption on the expansion rate, some domination condition, then you then this SRB measure has a natural extension to an SRB measure in. So this gives rise to an SRB measure mu, then I will denote this without the tilde for F. And this extra direction gives you an extra dimension in the tangent space. And this turns out to be the equilibrium state of some naturally defined potential, which gets an extra center direction. So in fact, the center direction would correspond to this direction, which was this unstable before, and you get an extra unstable direction. So the two directions in the tangent space define this bundle. And then the attractor still continues in this manifold, and this would be my saddle attractor. And the corresponding SRB measure we call saddle SRB measure, because it lives in the surface. It's an SRB measure, but it has some extension to the M in space where it has the saddle expansion property in the xi dimension. So this answers your question? No? Okay. Okay, so let me try to. So I take this surface on top with the construction is a bit more complicated because you need to find your cycle, and one important ingredient of my properties. Oh my dear, I erased the rich cycle. I erased the rich cycle? You did. Ah, what a shame. Sorry about this. Okay, so for the rich cycle, we need a set lambda which has a partially hyperbolic splitting. We need two measures of different type, which will be the SRB measure, and it will sit on this plane on top here. And then I also take an SRB measure for the inverse, and I place this in a plane which is, which is on this plane over here, and expanded correspondingly, extended by a strong, just reversing the directions. Okay, so the entire configuration is a bit more complicated. We start with a configuration of fixed points with these intersections of the manifolds, and then we do a surgery to replace the fixed point up there by my Plückchen attractor, and the other fixed point by another Plückchen attractor for the inverse. And we choose them such that the two planes intersect in this line. And then I mentioned that the Plückchen attractor has the property that the stable foliation foliates the entire space. So here there's in this curve there's a segment with positive Lebesgue measure of generic points for the SRB measure. And likewise, so this will be good. This will be here. And correspondingly, I find a set of generic points which fill a positive Lebesgue measure segment, so they have good intersection properties. Okay? So this is more or less the construction which needs to be done carefully because we need a globally defined partially hyperbolic set, which is a bit tricky for the construction, which I'm not going to explain. Okay, so let me just try to explain why these other properties are satisfied. The third condition was that the two measures are in a cycle, that for any point in the support of one, the stable, unstable intersect transversally any other point in the other. So let's just take any point in the support of the SRB measure down here, and it's strong unstable manifold. And by using some inclination lemma arguments, you see that this manifold, no? Someone erased the slide, okay. That this strong unstable manifold accumulates here and eventually intersects the unstable manifold of any other point in the support of the other measure, and vice versa when you change to the other measure. So this is a third property of the rich cycle is satisfied, and I indicated this already. Here it is. Okay, so here this continuation of this strong unstable manifold accumulates here and eventually accumulates here and intersects the stable manifold of any other point. Okay, so this is the third which was the third condition on this rich heterodimensional cycle. And the fourth condition, which is intersections between the manifolds of lower dimension. So as I said already here, and you have these strong stable manifolds which are generic for the saddle SRB measure up here, but they fill up here an entire positive Lebesgue measure segment, and they intersect. Some of them intersect. One of them, at least one of them, there are plenty in fact, intersect the strong unstable of generic points of the other SRB measures. So you have this saddle property, this cycle property, in fact, satisfied for plenty of points. And hence, you get this, which was the fourth condition of the rich cycle. Okay? So this is the first example, and in fact, this configuration is a robust configuration. So it is done for C2 diffeomorphism because you need DSRB measures and the continuous variation of DSRB measures. So for that, you need to assume C2, and the perturbation hence has also to be done in C2, but it gives you an example of a rich heterodimensional cycle, which is robust. Okay? Any questions? So I can come to my second playground, which are robust heterodimensional cycles from blenders. So as I said, this is not yet done for diffeomorphism. If you would like to put this in a general diffeomorphism setting, but there are some difficulties. So we studied first skew products. So our map is a skew product map, which in the first coordinate has a symbolic space, let's say in 4 coordinates, and then the remaining, the fibers is just R1. First coordinate is simple shift map, and according to the symbol, you have one of 4 fiber maps. So I don't know if you like my figure. Put lots of effort in it, but that's not the reason to like it, but I hope it illustrates. So in the base, you have the cylinders for the rectangles that eventually define your, represent your map, which is conjugate to the shift map, and the fibers. The fiber maps are, in the blue part, 2 contractions, F1, F2, and in the red, so in the all what fibers over this blue part, we apply one of these 2 maps, and in the red part, one of those 2 maps, which you just take the inverses. Okay, so these maps have some overlap. Here they have some overlap in some interval for F1 and F2, and also for F3 and F4. So if you look at the restriction, you ignore anything in red and just look at the subsystem, which is over the shift in 2 symbols. Sorry. Yes, I was. Yeah. Then you have 2 hyperbolic sets. There is the first intersection of the stable and unstable manifolds. The third property is trivially satisfied because of the product structure. And to make the cycle, the last property, you find generic points of one and of the others, who you need to make intersect these. You need to find good orbits such that, and good measures such that their strong manifolds intersect in some point. Sorry, sorry, I'm over time. That's awful.
Compactness in the fiber you define on R.
Huh?
You define on R the fiber. You don't need any compactness.
What do you mean compactness?
It define on R, not in an interval. They skip product.
The maximal invariant set will stay within some compact region. Okay? So now, what measures make this intersection? You recall what did Lasota-York, and you just look at this window, and you see a measure, an interval map, which has an absolutely continuous invariant measure on this interval, which has generic points, which have Lebesgue, the property that Lebesgue almost every point is generic, and then you take this interval map and extend this to a map on this skew product, and hence you get a measure whose projection to the fibers fills a full Lebesgue measure set. And you do this for the red part, you do this for the blue part, and hence you get in the projection 2 sets which intersect in plenty of points, and this gives the argument why you find these pairs of measures. In fact, there are plenty of measures which have this property, which have this pair of generic points, and this is our suggestion to study ergodic blenders. Okay, thank you. Sorry for the overtime.